Young set up a double slit experiment, so the schematic here is shown, where light propagates through two narrow slits, and the interference patterns produced by the interacting light propagating from these slits show that light has wave properties. So suppose we have a monochromatic light, such as a laser, so that has a particular wavelength, and this is incident on two slits that are a distance d apart. And the pattern on the screen is caused by a combination of wave diffraction and interference. And here we'll consider the pattern on the screen due to wave interference only. So remember when we looked at a single slit, each point on the wave was a source of spherical wavelets, and these interfere as the wavefront progresses. So this effect is ignored in our initial analysis, and it's reasonable to ignore it when the width of the slit is similar to the wavelength of the light source. So recall for a single slit, we had the distance to a minimum, which is a point of destructive interference, was equal to the index of the minimum by the wavelength of light by the distance to the screen over the width of the slit. So if the wavelength of light is similar to the width of the slit, and we looked at the first minimum from the center, then the width of the brightest spot, indicated by this red intensity curve, due to single slit diffraction, is quite large, so we won't get this diffraction pattern, consisting of bright spots with a drop in intensity. So as the width of the slit increases, then we can no longer ignore the diffraction effects due to the wavelets of light. So for this reason, it's reasonable to consider the pattern on the screen due to interference only, where the slit width is quite small. And now assuming the waves that propagate from these slits are coherent, so basically they're in the same phase, then as they propagate to the screen and interact with each other, we see that constructive and destructive interference of these wavefronts result in bright and dark bands on the screen. So as we can see, when the crests of the two waves line up, that's constructive interference, so that'll give a bright spot in the middle of the screen, opposite the middle of the slits, and between those points we have the peak of one wavefront interfering with the trough of the other, and therefore that gives dark bands on the screen between those bright bands. And this is the plot of intensity due to the interference between those two waves, which has a constant amplitude, as we can see. Now if we draw a ray from one slit to some point on the screen, and the other slit to the same point, and then we take a perpendicular line from the bottom ray, then we denote this distance over here as the additional distance that this wavefront has to travel compared to this one. And if we look at our horizontal line and take our angle theta to this line, so we'll take that as theta. So for the case where L is prominently larger than the distance between the slits, this angle is going to be quite small, and roughly equal to this angle. So therefore we have a right triangle here, and sine theta is equal to the additional distance that this wavefront has to travel, which is delta d, on the hypotenuse being the distance between the slits. So therefore, the path length difference between the wavefronts is d sine theta. So generally, we can write d sine theta being equal to m multiplied by the wavelength of light, and therefore to get a bright fringe of light, the path length difference between the wavefronts must be a multiple of the wavelength of light. So m equals 0, 1, 2, and so on. So the index m equals 0 indicates that the path length difference between the wavefronts is 0, and then for m equals 1, the path length difference between the wavefronts is lambda, and for m equals 2, the path length difference is 2 lambda, and so on. So remember, if we had two waves, and this wave was shifted a full wavelength, then these waves interfere constructively. So this is the case for constructive interference. And for destructive interference, we can rewrite this equation as d sine theta being equal to m plus a half by lambda, where m is a positive integer. So we see that when m equals 0, we get m plus 1/2 lambda, which refers to the location of the first minimum between those two bright fringes. And when m equals 1, we get 1.5 lambda, so that gives the next dark fringe, and so on. So this formula here is for destructive interference, where we use the same m indices. Now if we want the distance from the middle of the first bright fringe to another bright fringe, which will denote y max, then we have tan of this angle theta being equal to the opposite edge on the adjacent edge, being the distance to the screen. And for small angles less than 10 degrees, then tan theta is approximately sine theta. So therefore, using this formula for constructive interference, we take sine theta as y max on L, so we can write d by y max on L is approximately m lambda. So if you turn this equation around, we can write y max is approximately equal to m lambda by the distance to the screen on the distance between the slits. So as we can see, when m equals 0, the distance to the first bright spot is 0, and when m equals 1, we have the distance to the next bright spot, or next maximum, and so on. So these are our general equations that we'll be using. Now when we consider both wave interference and diffraction, then a double slit creates an interference pattern of maxima and minima that are superimposed within the envelope created by single-slit diffraction. So remember, for a single slit, we had the following envelope, and therefore in a double slit experiment, when we consider both diffraction effects and wave interference, then our intensity plot looks something like this. So we have a maximum here, and then a minimum, and then a maximum, and then a minimum, and this continues on and on. So we have a maximum, then a minimum, And then this maximum gets enveloped in a single slit diffraction envelope. And this pattern continues as follows. And we have the same thing on the other side. So that's the intensity we expect when we consider both diffraction and interference in a double slit experiment. So the intensity of these bright spots drops off. Recall that when we looked at single slit diffraction, we observed this first pattern on the screen for our monochromatic light source, where the bright bands are more smeared. And when we had two slits, the bright spots become more focused into points. And as you keep increasing the number of slits, the diffraction and interference between the light waves result in the bright spots being more focused. So diffraction grating is a collection of evenly spaced parallel slits or openings which produce an interference pattern being a combination of numerous diffraction patterns that are superimposed on top of each other. And diffraction gratings can consist of hundreds of openings per millimeter. So we call these lines per millimeter. So for example, if there were 700 lines per millimeter, you can multiply this by 1000 to get this in lines per meter. And then if you take the reciprocal, you'll be able to get the distance between two openings. So that's in the order of microns. So for example, if we consider some point on the screen and draw a ray from each slit to the screen. So remember that the light wave is going to be broken up into several waves that propagate from each opening, and they're going to diffract and interfere at the screen. So the relative distance that these waves have to travel has to be a multiple of a wavelength for them to constructively interfere. So essentially, d sine theta is equal to m lambda. So for the bright bands, m is a positive integer, starting from 0. So this is the same formula we had for the double slit experiment. And again we measure the angle theta from the middle of the openings. And theta is the angle between this horizontal line and this line over here to the mth order bright spot on the screen. And given that the distance to the screen is assumed to be much larger than the total distance between the openings, then these angles are taken to be approximately equal to theta, because the light rays are assumed virtually parallel. Now when we have white light that's incident on the gratings, that's going to comprise of different wavelengths, from red to violet, where red has the larger wavelength and violet has the smallest. So when m equals 0, the white light is not going to get dispersed. But as you keep increasing the angle theta, given the difference between the wavelengths of light, we see that red, having the larger wavelength, gets diffracted further than the violet light with the smaller wavelength. So as we can see, the light gets blurred as we move from m equals 0 to m equals 1. So this is the first order rainbow, and m equals 2 is the second order rainbow. So as we can see, for the red light, that gets diffracted as follows. and that's followed by orange, yellow, blue, and violet. So the center maximum is white, and the higher order maxima disperse the white light into rainbow colors, with the red light having the longest wavelength, appearing farthest from the central maximum. Young's double-slit experiment is conducted where the distance between the apertures is 2 mm. The distance to the screen is 8 meters, and the wavelength of light used is 490 nanometers. So let's draw a schematic of this problem. So we have our apertures in the middle, 2 mm apart, and the distance to the screen is 8 meters, and the wavelength of light is 490 nanometers. So in part A, we're asked for the distance to the third brightest fringe, below the center of the screen. So remember, we had the first bright fringe in the middle, and that's followed by the second, third, and so on. So m equals 0 represents the first bright fringe, and m equals 1 is the first order of maximum brightness, so that's the next fringe, and m equals 2 is the next order, and m equals 3 represents the next fringe. So this is the third brightest fringe, below the center of the screen. So we recall our formula, Y max, which is measured from the middle between the slits to the point on the screen that we're looking at. So in this case, we're measuring theta to this fringe over here. So that was approximately equal to m, which is the third order fringe we're looking at, multiplied by the wavelength of light, which we'll convert to meters, multiplied by the distance from the slits to the screen, and that's divided by the distance between the apertures. So we'll convert from millimeters to meters. So that gives 5.88 by 10 to the minus 3 meters, or 5.88 millimeters, which is this distance over here. Now in part B, we're asked for the distance to the first dark fringe above the center of the screen. So m equals 1 is the next bright spot above the screen, and the dark spot is m equal to 0 plus a half. So what we get is Y min being approximately 0 plus a half by the wavelength of light in meters by the distance to the screen. And that's divided by the distance between the apertures. So that gives 9.8 by 10 to the minus 4 meters, or 0.98 millimeters. And part C asks how the interference pattern would be affected if the slits were moved further apart. So if the distance between the slits increases, then the distance to the fringes from the central maximum decreases. So the fringes become smaller, and the bright and dark spots get more squished together. A diffraction grating experiment is conducted with 500 lines per millimeter. So we have many slits or gratings where the light passes through. And white light is used with two given wavelengths, being the wavelengths of red and violet light. And we're asked to determine the angular separation between the red and violet bright spots in the second rainbow above the central maximum. So recall that the white light doesn't get diffracted in the middle, but then due to the difference in path length of the waves above this central maximum at m equals 0, the red light gets diffracted the most due to its higher wavelength, and the violet light gets diffracted the least. And that's in accordance with this formula, being the distance between the gratings multiplied by the sine of the angle from the horizontal line of the central maximum to a point on the screen that we're looking at. And that's equal to the mth order of brightness by the wavelength of light. So here we have 500 lines or gratings per millimeter. So we can convert this into lines per meter. So that'll be 500,000. And then the distance between the gratings is the reciprocal of 500 by 10 cubed. So that would give us a distance of meters per line, which is 2 by 10 to the minus 6 meters, or 2 micrometers. So therefore, sine of the angle between the horizontal and the line to a red bright spot for the second rainbow. So we have m equals 1 for the first rainbow and m equals 2 for the second rainbow. So that would be 2 multiplied by the wavelength of red light, which is 620 nanometers by 10 to the minus 9 meters, over the distance between the gratings. So that would be 2 by 10 to the minus 6 meters. So calculating this out gives 0.62. And taking the arc sine of 0.62 gives theta r as 38.3 degrees. And for the violet light, we would just replace the wavelength in this expression with 460 nanometers. So if you calculate this out, you'd get 0.46, and taking the arc sine would give you an angle for the violet light of 27.4 degrees. So as expected, the red light gets refracted more than a violet light. And therefore the angular separation between the red and violet spots is the difference between the two angles, which is around 11 degrees. And this is not drawn to scale, so if you do the same calculation for m equals 1, the angular separation between these two spots is going to be smaller, given the rainbow gets dispersed more as we move away from the central maximum.